Welcome to today's PCM webinar dedicated on a nice topic, PCP, myth and truth. So thank you for taking your time to join us today, and also sorry for the late sending of the invitation. So I hope every people who wanted to attend receive the register link. My name is Benjamin Robert. I'm in charge of operation at PCM for 12 years. And today I would like to introduce the presenter for this webinar, Paul Skoczylas. So Paul has a great experience in oil and gas and is recognized as an expert in the artificial lift sector and especially in a progressing cavity pump. So after more than 20 years working in Canada, it's a pleasure to have Paul here in PCM as a ALS product champion for almost 1 year now. So you are here today because most of you certainly heard many things about PCP and you are not sure whether it's true or false. This is why we decided to prepare a series of beliefs, and we'll tell you if it's whether a myth or a truth. Also, we'd love to hear from you, so feel free to ask your question in a dedicated Q&A section on the right part of the screen normally. Then after, with Paul, we'll answer the question after the presentation that will take about 20 to 30 minutes. Also, don't worry, a recorded version on this webinar, including the show slides, will be available on our LinkedIn page and also on our website, pcmals.com, within a couple of days after the presentation. So we'll start very soon with Paul. Just for those who just join us, welcome again. Sorry for the late sending of the link. So Paul will provide answer on most common beliefs about artificial lift PCP, and then after we'll answer your question. Paul, I think it's your time now.
Okay, thank you. I hope everyone can hear me fine. If there's any problems, use the Q&A and Benjamin will be watching that and will let me know if there's any problems. Again, with the Q&A, you can type in your questions into that Q&A section at any time, and when we get to the end of the presentation, we'll go through the questions that have been entered. So we at PCM, all of us in the artificial lift side, we came up with a fairly long list of myths and truths, and today we're going to cover the first half of that list. We have some more that we maybe save till next month or something like that. We'll schedule a later session, but here's the ones we're going to talk about today, and I'll go through each of these and say, is it a myth or a truth? Or quite often, even the things that are myth are usually based in some element of truth, so we can talk about that a little bit as well. All right, so on that we can just move straight into the first one. The myth says you need 1 foot of space out for every 1,000 feet of rods. Is that true? Well, no, not really. I've heard variations on this. This one's this 1 foot per 1,000 feet is a myth that one of the guys at PCM has heard. I've heard various numbers depending on where I go around the world, anywhere from 2 inches per 1,000 feet up to the 1 foot. And really, it depends on a lot of things. The space out depends on the pump model, the pressure, the rod size, etc. So most PCP companies will provide a chart for calculating this, or for telling you, for this pump model at this pressure with this rod size, this is how much space out you need per 1,000 feet or per 1,000 meters of rods. And then most people will put some safety factor on there, calculate the theoretical space out and then add 6 inches or whatever. Those rules of thumb, again, this 1 foot or 2 inches or whatever your rule of thumb is for your area, might be okay for a particular field. If you're all one rod size and one pump size, yeah, the number is going to be fairly consistent. But as soon as you go to a different pump or a different rod, then those numbers can change. So here's just some examples on here for PCM pumps. So our smallest displacement pump at high pressure might need 2 or 3 inches per 1,000 feet. And our biggest pump, or one of our biggest pumps at high pressure, might need 8 inches per 1,000 feet. So neither of those is actually getting up to the 1 foot. Now, if you use that big pump with 1-inch rods, then yeah, it's probably going to get to a foot, but you're probably overloading your rods there anyway. These calculations are all based on the well being pumped off, so low intake pressure, and that'll be the worst case. So even with the same differential pressure on the pump, if the intake pressure is higher, there's actually need less space out. Most of the tables that the companies will provide won't consider that. It'll be under under pump off conditions. But if you're using the software, whether that's PCM design that we have here or other software available on the market that you're familiar with, the software will usually calculate under the actual conditions, what's the intake pressure, what's the discharge pressure, what's the geometry of the rod string and the geometry of the pump, and calculate the actual required space out. So if you really want accurate numbers, then that's what you would do. But the tables are pretty good and gives you the worst case. So move on to the next one. All metal PCP cannot pump water. I think there's some basis here. Obviously, everybody knows that an all metal PCP has clearance inside it, so it doesn't have a interference fit the way an elastomeric pump does. But does that mean it can't pump water? Well, let's say yes and no. It's going to be less efficient, but it certainly can pump water, absolutely. But it's just the efficiency is going to be less. So when you're running an all metal PCP, you can expect to have lower volumetric efficiency. How low will depend on various things like the viscosity of the fluid. If you're in a heavy oil application and the temperature comes down, say at the end of a CSS cycle, for example, when the viscosity is higher, the efficiency can be pretty good. A lot of all metal PCPs are used in SAGD. In SAGD applications, the temperature is pretty high, and the viscosity of the oil at that high temperature is actually pretty similar to water at room temperature, about 1 centipoise. And the AMPCPs work just fine. So the low viscosity is not a problem. It's just that you do have to accept lower efficiency, and that's all. The PCM Vulcane all metal PCPs, before they leave the factory here, they're tested, and they will have more than 55% efficiency at 300 RPM in full head. And in fact, that's the acceptance criteria. Most of the pumps we're making right now have between 60 and 65% under those conditions. So it's actually pretty good. And that's at full head. So most people, you're not running this at full head, so you're actually going to have slightly better. We know that in time the efficiency goes down. Pump wears out a little bit, and there's a bit of a break-in period where the efficiency will drop fairly quickly, and then it stabilizes. So you can get good performance out of an all-metal PC pump. You just have to accept that the efficiency is going to be less than an elastomeric pump. Low PCP volumetric efficiency while operating the well is always bad. Well, it's a myth that it's always bad. It can be bad. Under some circumstances, it can certainly be bad, but not always. It depends on conditions again. So we're talking about efficiency in the well here, not on the bench test. We have a myth that we'll talk about in the next session, next month, about efficiency on the bench test. So, in fact, volumetric efficiency that's too high may be bad in some cases, depending on why it's too high. If the pump is too tight, for example, that's just high friction, it's wasted power, you're generating heat that's bad for the pump, and it can make the pump last actually less than if it was looser. So there's typically an optimum volumetric efficiency that you'd like to be operating at, but again, circumstances that can change depending on what the fluids are and what the geometry is, etc. So particularly when you start dealing with viscous oil, you can have a very loose pump and still have very high efficiency, and that's just fine. But the big question here, for when we're asking the question of how low can the efficiency go, people always want to ask the question, how low can the efficiency be before it's bad, before it's bad for the pump? And there isn't a single answer to that question. You have to look at, is there enough liquid going through the pump to remove all the heat being generated? whether it's by friction or hysteresis or gas compression or whatever's generating heat inside the pump, mostly by friction. So this depends on a bunch of factors. They're listed there. So the higher the friction torque, obviously, the more heat's being generated. The higher the speed, the more heat's being generated. What's the elastomer's maximum temperature? If you're in a 20 degrees Celsius well and your elastomer is rated to 80 degrees C, you can get by with a lot more heat generation than if, for the same elastomer, if your well was 65 or 70 degrees C, you've got a lot less room there. So it depends on how far you are from that temperature. The type of the fluid. Water is great at removing heat. Water is the best at removing heat. Oil is not as good at water. Water can remove 2 to 3 times as much heat as oil can. So if you're in a high water cut application, you can get by with lower efficiencies than if you're in oil. Gas, when you have gas bubbles or free gas slugs or whatever going through the pump, gas is really bad at carrying away heat. So the more gas you've got going through the pump, the more careful you have to be with your efficiencies. And a slug of gas now and then is not a big deal, but if it's continuous, then it's not carrying away the heat. And lastly, I've got in there what's the pressure and temperature distribution inside the pump. So typically the top of the pump does more work than the bottom, so that's where the damage from high temperature usually happens. So if you can by selecting your pump properly, make that distribution more uniform. And again, this is why one of the reasons why an efficiency that's too high can be bad, because it forces the top of the pump to do all that work. A looser pump can spread that out. If you're dealing specifically with gas, when you have gas going through the pump, it definitely has higher pressure at the top, and that's what the PCM slugger is designed to. What we used to call the PCP is designed to improve that pressure distribution when there's a lot of gas. So there's ways to deal with that. Next one, PCPs do not gas lock. So is this myth or is this a truth? And we think it's a truth. So it comes down to the question, I guess, is what is gas locking? And that gets really complicated. When we start talking about gas lock, it's when there's still power going to the pump, but nothing's moving in it. And it can happen in beam pumps, so the reciprocating pumps, and it can happen in ESPs. And the physics in those two situations are very different from each other, but the end result is the same. The pump is running, but there's no fluid moving. So in a rod pump, basically what happens is the pressures are just right. When the plunger goes down, if there's gas in there, if the space is filled with gas and the plunger goes down, it might not have compressed that gas enough to open the traveling valve. And then when the plunger goes up, it might not expand enough, the gas in there might not expand enough to allow the standing valve to open. So basically the plunger is just moving up and down and the valves aren't opening, so no fluid is moving. So that depends, obviously you have to have a lot of gas inside the plunger for that to happen, and it has to have the right pressures in the tubing and at the reservoir. But that's a problem that is fairly common in beam pump situations with high gas. In an ESP, it's completely different, of course. There's no valves, just like in a PCP where there's no valves. So it's not a question of valves opening and closing. But an ESP is a centrifugal pump, and those generate head, not pressure. So what's the distinct difference between head and pressure? The difference is based on the density of the fluid. So when you look at a performance curve for an ESP, it doesn't have pressure on the vertical axis, it has head. And it turns out it doesn't matter what the fluid going through it is, whether it's water or oil or gas, it'll produce the same head of that fluid. So for an example, if you have a pump that can produce 10 megapascals of pressure, so 1,000 meters of head is 10 megapascals of pressure with water. It might be 8 megapascals with oil, but it's less than 1 megapascal with gas. So if you have slug of gas going through that ESP, now it's only able to produce less than 1 MPa, but the tubing's filled with water or oil, so there's 8 or 10 MPa of pressure that's required to move it, so nothing moves. It's the ESP is no longer capable of moving that fluid if it fills with gas. And this is a bit of a simplification because, in fact, in multi-phase flow in an ESP, you get other things going on like surging, so it gets very complicated. But the basic physics is still the same. That an ESP can't generate pressure when it has gas going through it. Of course, with both rod pumps and ESPs, they've come up with new designs, different valve designs, for example, in a rod pump, or different impeller designs for an ESP to try to combat these problems. And there's pump designs which can do better and be more resistant to gas lock, but the fact of the matter is that both rod pumps and ESPs are subject to gas locking. A PCP does not have either of these problems. There's no valves, the cavity's just open, capture some fluid and move it to the top and discharge it. So the fluid will continue to move through the pump as long as that pump is rotating and the seals are intact inside the pump. So it's the end result is that the PCP will not gas lock. Now, obviously, if you're having 100% gas coming into a pump, even an HR PCP will not like 100% gas for a sustained period of time. But when you have a slug of gas coming through, or just a large amount of GVF over time, the PCP can certainly do that. The next myth we have says no backspin after a stop. So when an operator stops the well, if he doesn't see any backspin, it means the rods must be broken. Well, is that true? Sometimes, sure, but not always. It's not a guarantee that the rods are broken. There could be other things happening here as well. So as I said, certainly broken rods, there'll be no backspin, but there could be some other things. So if you have a hole in tubing or broken tubing, or since I know there's a bunch of people from Australia here, I know some people there are running the automatic drain valves. Any of those things means the fluid will drain out through the hole in the tubing, through the broken tubing, or through the drain valve. And if it's not draining through the pump, then it's not going to turn the rods backward. So much less backspin there. If you have a very loose pump, or a pump that's badly worn, or it's suffered catastrophic failure to the elastomer, the fluid will just drain right through it, again, without forcing the rotor to turn, so no backspin. If you have a very high fluid level, I've seen this in some wells, in water floods, for example, where there's a lot of fluid in the well. The pump's not working very hard, and the friction torque of the pump is enough to actually hold that fluid level, in which case no fluid drains through the pump and you get very little backspin. So some of these causes will show a few turns because there's twist in the rod still that will come out, but it takes a couple of seconds maybe for that backspin to come out of the rods. So if the operator presses the stop button on the panel and then turns to look at the drive head, by the time he turns and looks at it, the backspin could be over and he might not see it. So if he doesn't see it, maybe he assumes that the rods are broken, but they might not be. And there's a safety aspect here, because if the operator thinks the rods are broken and tells the rig crew that, they might not be careful when they lift the rods up, thinking that they're just broken, they'll just come up. But because if there is any retained torque in the pump, if it's holding any fluid there and the rods are not broken, when you start lifting that rod up, it's going to start rotating. And the rig crews are usually, they're trained in this, and that it shouldn't usually be a problem. Although I know I've shared with some people, there's a YouTube video out there, and if you ask me offline, I can send you the link for it. But it's not my video; it's just one that's on YouTube. But it shows exactly what happens when a rig crew lifts up a rod when there's retained fluid, and it's not something you want to be involved in on a rig. So yes, always be cautious of retained torque. Even if you think the rods are broken, assume they're not, and proceed with caution. So the PCP is not a good choice for pumping high API oil. Is that true or false? Well, I'm going to say false, but it's one of these myths that has a basis in fact. Certainly 20, 30 years ago, it could have been true, but elastomers have come a long way since then. High API oil is not always the first choice for PCPs. The PCP is really, it's a heavy oil pump. It does great in heavy oil. It does great in solids, but it can certainly be used in other applications, and it very often is used in other applications because it's a low cost and high efficiency pumping system. It's just that in heavy oil or solids applications, those are where other artificial lift systems simply don't work or not very well. So the PCP really stands out there. And the PCPs can certainly use in other applications. It's just now they're competing with the other systems based on cost instead of technical factors. So going into a high API well, especially if there's gas there where you're having gas lock, and we covered gas lock already, then the PCP certainly can be a good choice. The problem with high API, especially going back to elastomers from 20 or 30 years ago, is aromatics. Typically, high API oils have more aromatics. And they'll talk about BTECs for benzene, ethylbenzene, toluene, and xylene, which are the monoaromatic hydrocarbons, they call them, because there's other polyaromatic, polycyclic aromatic hydrocarbons, I think they're called as well, which aren't as bad. But these BTECs aromatics can often be a problem for elastomers. There's a correlation between high API and high aromatics, but it's not a perfect correlation. So if you have a high API field, you should check what is the aromatic content of that fluid. There are some fields where the API is high, but the aromatics are low, and PCPs can do just fine there. If there are high aromatics, you do need to be very careful with elastomer selection. The elastomers today are certainly better than what we had 30 years ago. And some of them can be okay for aromatics, again, as long as maybe the temperature is not too high, or you don't also have H2S or CO2 or things like that. These are, we can work with you on these, and most PCP suppliers can come up with some option, unless the aromatics are just too high. So again, it's work with your elastomer suppliers or your PCP supplier, and we can certainly try and advise on which elastomers might be the best for your particular application. So here's one: explosive decompression. The idea here is slow, stop, and pull. If POOH means pull out of hole, if you haven't seen that one before. So slow, stop, and pull to reduce the risk of explosive decompression. So if you know you're stopping the well and you think you might have a problem with explosive decompression, the theory is let's slow it down over time instead of just stopping it, and then when we're pulling it, pull it really slowly. So I'm going to say myth. In theory, this might work. In practice, it's just not practical. It can take days for the bubbles to appear. So are you going to slow your pump down and pull it over the period of a week? Probably not. You want your rig crew out there pulling 1 rod per hour to do it nice and slowly, or even even slower than that. So in the little animation you can see here, this is a stator it's obviously been out of the well for a while because it's been taken to the lab and cut apart. And you can see the guy sticking a needle into it, and when the needle hits a bubble of CO2, the syringe pops up. So there's still a lot of gas trapped in that rubber days later. So yeah, if you doing your pull over a few hours is not going to affect your explosive decompression at all. It would have to be over days, and even then I'm not sure that it would work. So some people have gone the other way. Then it's okay, if this takes days for it to happen, let's pull the pumps out of the ground, put end caps on them and pressure them up so then they won't be damaged from explosive decompression. Well, and I guess you could slowly depressure them over a period of as long as you want then. Is that a good idea? Technically it might work, but I really don't like the idea of keeping pressurized stators in my warehouse. That's just for safety reasons. I think that's a really bad idea. So I would not recommend that, and I don't know that it's going to work 100% of the time either. So explosive decompression is just the problem that we have to deal with. We deal with it by trying to keep the gas away from the pump if possible. If you can have the gas go up the annulus, that's better. If there's going to be CO2 going through the pump, then we're choosing an elastomer that is most resistant to that CO2 and the explosive decompression. That's the way we deal with this, not by our stopping and pulling practices. So that's our first list. So that's about 20-25 minutes worth of PCP myths here that we'll go through. We'll do another 25 minutes next month, I think. So here's a list of on this slide, it's a list of the ones we're going to get to next month. So there's a lot of beliefs about PCPs, and some of them are true. Some of them are maybe were true in the past. Some of them might just be oversimplified. So just being very careful in how we interpret these and make decisions based on them. So I hope that some of the things I've gone over today have been helpful. If you need support, if you've got workover crews or completions people who still believe some of these things that maybe need some education, we're certainly very happy here at PCM to talk with people or provide some more detailed information on this, and we can provide some references or resources to help you with these as well. So in terms of questions, I'd appreciate if you could restrict the questions to just the topics in today's webinar. If you've got some for the ones that are on that list there for next time, I'll be happy to listen to you next time. Or if you have any other questions at all about anything, contact me offline. I'm always happy to talk to people about PCPs, anything at all to do with PCPs. So if you have any questions, please just contact me by email. But for anything on today's topics, we'll go into the Q&A session now. The last slide just has my email address and our website there. So yeah, all right, I'm going to pull up my Q&A tab now. I'll just leave that slide up so everyone can see it, and we'll see what questions have come through here. So the first question is, what is the maximum GOR that a PCP can handle, and what type of elastomer? We were actually just discussing this yesterday in terms of, well, we were talking about our HR PCP or slugger pump. But really, it's not a question of the GOR, because with the GOR, that's the total gas coming out of the well divided by the total oil coming out of the well. If the gas doesn't go through the pump doesn't care about it. You could have a very high GOR, but if the pump is down below the perforations and you've got good separation, very little of that gas goes through the pump, so it doesn't matter. Or you could actually have the opposite. You could have a well with a low GOR, but the pump is above the perforations and the geometry is such that there's poor separation and you get a lot of gas going through the pump and it's worse. So it's not a question of what's the maximum GOR. It's a question of what's the GVF going into the pump. So what's of the volume of the pump at the pump intake, how much of that volume is gas under the in situ conditions and how much is liquid. And typically for a normal PCP, again, go back to that slide I talked about efficiencies, because that's the same thing, right? You need to have enough liquid going through the pump to keep it cool. So it will depend on factors like temperature and whether it's oil or water and things like that. But typically for a normal PCP, people will use numbers in the range of 30 to 50% GVF at the pump intake as a maximum. If you're going to the slugger design, the HR PCP from PCM, we'll advertise that it's good to maybe 85% GVF continuous, and it can take slugs of higher for short periods, of course. But even that 85% is going to depend on things like your temperature and whether it's oil and water and things like that. But those are ballpark numbers. So I always work on GVF for when we're talking about what a PCP can handle. And what type of elastomer? Again, some elastomers are better for gas than others. So again, talk with your vendor, whether that's us or, and it's not me. I'm not the elastomer expert. But certainly we can, the people who are here who know more about the elastomers. I've only been at PCM a year, so I still haven't memorized which elastomer is which here. So, but yeah, some of them are better for gas than others, especially if there's CO2 in there. So for sure, yeah, you need to consider that. But so I hope I've answered that in terms of GVF and not GOR, because again, it's the separation in the well determines whether a high GOR can also be a high GOF or not. The next question here is, does it mean that PCP is not affected by high API? What about waxy crude oil? Okay, really, it's in terms of the PCP itself and the elastomer, it's really that the aromatics content that matters. And like I said, there's a correlation with API on that. For things like waxy crudes, well, you got other problems there. It's not the pump that's the problem. Usually with the waxy crudes, it's the wax builds up on the tubing walls and blocks the flow eventually, and that'll be a problem with any pump. So yeah, those are other problems that you definitely have to deal with. With a beam pumping application, they put scrapers on the rods, and as the rods go up and down, they scrape the wax off. And obviously, you can't do that in a PCP application because the rods are rotating. So anything you put on the rod will only rotate in that one spot. So I know the temperature is something that people will do, and there were some fields that I'm aware of where they pumped hot water down the wells to keep the temperature in the tubing high enough to prevent wax from forming. So you deal with other things. Now you're pumping hot water down the well. It's high enough to melt wax. What's it doing to the PC pump elastomer? So you need to make sure that you've chosen an appropriate elastomer for that temperature. Typically, that's not a problem because usually that wax temperature, at least in the field that I was aware of, it was around 55 degrees or something like that. So the elastomers can certainly handle that. You just have to be cautious and not to put the water too hot. Am I missing something here? Or are those the only questions? Where's my? Oh wait, no, there's another one here. What is the deepest pumps can set with high flow reaching the surface? Well, that's usually the trade-off with a PCP or really with any pumping system. The higher the flow that you want, probably the shallower it's going to be able to get that flow. And I don't have the numbers memorized, and part of it will be based on your casing size, but really it's a question of the power you need to deliver to the pump, and more importantly the torque. The biggest rods on the market are capable of doing about 3,000 foot-pounds safely. They're rated for a little higher than that, but downgrade to 80% of the published rating and you get 3,000 foot-pounds. So it's a question of what can you get out of 3,000 foot-pounds. If you put a really big pump in there, then you'll get very high flow, but it'll have lower pressure. Or I can put a smaller pump in there and have really high pressure on it, but lower flow, and still be at that 3,000 foot-pound limit. So that's really, you end up with a curve there that's that the curve goes to low pressure and high flow to high pressure and low flow. So I mean, people will talk about PCPs that are installed down at 3,000 meters or more, but you're not getting very high flow out of that. And then there's other PCPs that are installed at, I know there's some in Australia right now that are installed maybe just a couple hundred meters deep, and they're pumping 5,000 barrels a day out of those wells. So it's again, shallow wells you get high flow, deep wells are lower. It'll depend on your casing size and tubing sizes, etc. Because what pump and what rods can you fit in there? So there isn't a single answer to that question. But you can look at for example, if you just go on any pump companies published list of pumps, you'll see that they're really big pumps that they sell probably have lower pressure ratings on them than the really small pumps, and it comes with the simple reason of what can you actually, how much power can you get to that pump through a rod string. So that again, I don't have numbers to answer your question, but so like I said, you can certainly have pumps that are more than 3,000 meters deep, but the flow rate's going to be low. And you can have pumps with very high flow, I mean 5,000 barrels a day. Theoretically, you can get a lot more than that if you have one of these really, really big pumps at very shallow depths and get good efficiency out of them. You can probably get what about maybe 8,000 barrels. I don't know, something like that. But yeah, you're not going to get that from any kind of depth. So I hope I've answered that question. More or less. I know it's not a number, but I hope I at least told you how you can get the right answer for your particular application. And again, if you've got a specific application you want us to look at, if you want to get a certain flow out of a well, send us the information about the well, and we'll look to see what we can do to help you get the highest flow out of that. Okay, there's more questions here now. Is explosive decompression only caused by CO2? Mostly. I don't want to say only. For explosive decompression to happen, the gas molecules have to be small enough to get into the rubber and to have enough of them in the rubber to cause problems. So CO2 is a small molecule, so yeah, it'll do that. Methane is a slightly larger molecule than CO2. It's not particularly large, so you might get methane happening a little bit, but much less than CO2. But any other gases that you're going to find in an oil well, the molecules just get too big and you get very little of it. So CO2 is certainly the biggest one that we see that can do that. How much sand percentage can a PCP handle? Well, in Canada, in the CHOPS wells there, for short periods of time, they're running 50% sand, certainly 30% for longer, and 4 or 5% for years. So, yeah, the PCP can handle some pretty high sand, but when you have those high sand rates, especially with the 30-50% range, those pumps are lasting a few months and then they're garbage. So it's if you want a pump that's going to last for 10 years, you better have very low sand in it. But they can certainly pump large quantities of sand for relatively short periods of time. It's just in those CHOPS wells, they accept that the sand production is part of the business of getting that very viscous oil, tens of thousands of centipoise. To get that out of the reservoir, it has to come with the sand. So they accept that as part of doing business. So yeah, I hope that answers that question. Can I explain what is explosive decompression? Oh, okay, I guess that was a term that not everybody's familiar with. Basically, the short description is, I'll use CO2 because it's the biggest culprit. Under pressure down in the well, CO2 is coming through the pump along with the gas and oil. Some of that CO2 diffuses into the rubber. When you depressure the pump, usually by bringing it to surface, in very extreme cases, it can be just shutting the well off as well. But I think most of the time it happens when you bring it to surface. The depressuring, the CO2 can't come out of the rubber as fast as it would like to, and it tears the rubber and causes blisters. So if you see blisters on a pump when it's been cut open or when you're doing a boroscope inspection, that's explosive decompression. Does a rod drop when the pump is running? If it hits the tag bar when running, what damage would it do? So either if it wasn't spaced out properly or if the polished rod clamp wasn't tightened properly, and the rod drops when it hits the tag bar, or so it's actually the rotor hitting the tag bar, of course. That can. I had a picture that was sent to me. I should have included in the space out drawing, but yeah, if your rods aren't spaced out properly or not high enough, or polished rod clamp slips, and the rod hits the tag bar, the rotor hits the tag bar and keeps running, it can actually drill all the way through that tag bar. So by itself, is that a major problem? Well, it's not good for the pump, obviously. It's not good for the rotor. Rotors will break. Quite often, if the rotor is running on the tag bar, the rotor will break. It doesn't always happen. Like I said, sometimes it'll break the tag bar instead. I have seen 2 cases, however. If it's happened twice, I'm sure it's happened more. It's just the 2 that I've seen pictures of from very different applications. One was heavy oil Venezuela, one was coal seam gas in Australia. But the results were the same in both cases. The rotor was running on the tag bar and broke the tag bar. And the broken tag bar apparently acted like or the rotor going into that broken tag bar acted like a screw going into a nut, and it pulled it down, like huge amounts of force pulling down through the rotation of it, and it jammed the rotor into the no-turn tool, even though the no-turn tool diameter was less than the rotor major diameter, and it jammed it in there so tight that it had to be, it had to come out with the tubing and be cut apart. So yeah, bad things can happen. The most common thing you're going to see running on the tag bar is a broken rotor, though. So yeah, it's definitely not good. Next question: does workload, rod load, or motor load show us what's happening with fluid level? Is it dependent on with pressure on pump intake? Short answer is yes. The long answer is you're never going to measure it with enough accuracy to use that for pump off control. So, so yes and no. In a perfect world, if everything was nice and consistent and you could measure pressures and torques perfectly, yeah, you could use that. And I know there's VFDs out there that will actually say they can do it. But when I've looked at the numbers in the past, the sensitivity is not there. Depending on what size of pump you've got and some other well conditions, you might need to have 200 meters of fluid above your pump to keep it safe within the error bars of that measurement, which it's just not reasonable for pump off control. The bigger the pump, the more accurate you're going to get with using torque for that. But for a small pump, it's just not. And then you got things like, well, the pump swells up and it changes the friction torque. So you see the torque increasing. Is that because the fluid level is going down, or is it because the pump is swelling, or you get some sand going through it, or whatever? So yeah, I'm not a fan of using rod load to measure fluid level. Having said that, there's a company that they sold drive heads in Venezuela. It's a company out of the United States. This was 20 years ago, and I think they're still in business, whether they still make this drive head or not, but it was a drive head that had a load cell built into it, so it would use axial load instead of torque. And using axial load, I mean, it makes it more accurate. The friction doesn't matter anymore, for example, but it's still, I think the sensitivity is probably small. But if it was in Venezuela, it was probably for big pumps, and maybe it was okay. But there's a paper on that's out there from 20 years ago. But yeah, so in general, I'm going to say no. I'm not going to recommend using load, rod or motor load to tell you what's happening with fluid level. That's my opinion anyway. All metal PCP can run with higher RPM for high API wells. Cavity with fluid. So a couple of questions there, I guess, in regards to all metal PCPs and cavity fillage. At PCM, we're not going to recommend running the all metal pumps at high speeds because of wear. I think historically they've been shown they last longer if you keep the speed below, I think, 300. I'm not sure what our official recommendation is here, but I've certainly heard that number from some of the people using it in Canada. That will help increase the life of those pumps, especially in the SAGD application. So normally we're not going to recommend running a metal PCP at high speed, so leave that out. Now, if you're using a metal pump in an oil application because the fluids are really nasty for your elastomer and you want to try using a metal pump instead, I know some people have done that. Again, I'm going to still go with the same speed recommendation there because again, it's metal rubbing on metal, and you're going to have wear. So I would keep that speed down. For cavity fillage, this is the same for any pump, whether it's metal or elastomer. Cavity fillage, the higher the speed, the more of a problem that can be, but it's going to depend on what's the pump geometry. So short pitch pumps are better if you're worried about cavity fillage. It's going to depend on the fluid viscosity. If you have a low viscosity fluid, I'm usually not worried about cavity fillage. High viscosity fluid is where it's a problem. And it's going to depend on intake pressure. So if you're fully pumped off and the pressure is low, it's more of a problem than if you've got lots of intake pressure that can help push that fluid into the pump. So again, that's a case where there's a whole bunch of what ifs in there. It depends on a bunch of different things if you're going to have cavity fillage or not. And again, if you're worried about that, most companies offer short pitch pump options. Some people call them the fat boy. At PCM, if you look in our list of pumps, we'll call them the heavy lift pumps that have shorter pitches that are better for viscous oil, solids, and just in generally cavity fillage issues. That's the same question again. Let's see. Can you do pump analysis by amperage chart from the VSD like with the ESP? To some extent, yeah, so this kind of goes back to what I was talking about before. You're looking at current to see what's happening in the pump. You can see some things happening there for sure. You can look at overall trends over time and try and interpret. The more information you have, is that if all you have is the current from the VFD, which tells you torque, it's kind of hard to get anything. But if you can add in flow rate measurements, pressure measurements, especially even if you don't have downhole pressure, let's make sure we know at least what the casing and tubing head pressures are. Because those things, if that's changing, well, it could change the torque, but it's got nothing to do with what's happening at the pump. But again, like I said, if everything at surface is constant, but you see the current increasing, does that mean you're pumping the well off, or does that mean that there's the friction's going up because of pump swell or solids accumulation? It's hard to answer that question, but based on just the data. But other field experience can be very useful for that. If you know in this field that there's no sand and the pumps tend to swell up over a period of a few weeks and then stabilize, then if it's following that trend, great. If it's not following the usual trend, then you start asking some questions. So sometimes that information is very useful. Sometimes it makes you ask more questions, and then you have to go out and try and find the answers to those. So yes, you can do some analysis. The more information you have, the more analysis you can do, of course. Sometimes you need to set the PCP under the perf, do low influx. Can I do that? Absolutely. I recommend it. Normally I would put the pumps below the perforations if at all possible. Definitely helps with gas. If the pump's below the perforations, you get much less gas going down to the pump intake because the gas tends to go up. It's not guaranteed. You could, especially at higher velocities or in a tight casing, you might see some of the gas being pulled down, but you're going to have definitely better separation when the pump's below the perforations. Deeper the pump, the higher the intake pressure. That's better for the pump as well. If you're in a really heavy solids application, that can actually still be good. You're going to have the solids going through the pump, yes, but that means the pump is going to be keeping the perforations clear of solids. If your pump's above the perforation, you get a lot of solids production. Anything that doesn't get produced is going to sit there, and it's eventually going to plug up your perforations, and you've got to come out and do a clean out. So there's lots of reasons to put the pump below the perforation. So I'm all in favor of that. And except in the solids case, it'll generally improve your pump run life. Again, higher intake pressure and less gas going through the pump, both good things. What are the most common reasons for not having flow at the wellhead besides tubing holes and rod breakage? Well, those are two. Either that or the pump is completely failed, or there's nothing coming in from the perforations. If something plugged up in the well, again, talk about solids plugging up the well. Those are pretty much your options. If there's fluid coming into the well and the pump is working, then hole and rod and tubing are the only things. If the pump's not working, well, there's your answer. And if there's no fluid coming into the well, that's the answer. So I'm sure there might be some other things people can think of, but yeah, tubing holes, rod breakage, the next thing you're looking at is the pump. And then finally the reservoir. Can metal-to-metal PCP operate with sand? It's a good question. Yes, it can. Will it last very long doing so? Probably not. So you're never going to get rid of all the sand. So even the SAGD operations in Canada, that's in sand. They're using slotted liners generally to keep as much of the sand as possible out of the pump, but there's always fines. So there is some solids going through those pumps, and they don't last forever. The efficiency does drop. But if you're having uncontrolled sand going through them, if for example the slotted liner fails and you get a lot of sand coming in, it's pretty clear those pumps are not going to last very long. So can a metal-to-metal pump operate with sand? Yes, but it's not going to last as long, and we would always recommend keeping the sand out of those metal PCPs. Does PCP and light oil with high API only depend on aromatic? Aromatics is the big one. The other one, of course, is gas. The more gas you have, you're worrying about you have too much gas going through the pump, especially if you're not running a slugger pump. Elastomer selection, if you're having CO2 and H2S, again, more likely with the high API, then you're making sure you're dealing with those problems as well. But certainly in terms of the elastomer itself, I think the aromatics is the biggest factor there. But again, H2S, CO2, and overall gas content are also factors as well. Can pump off condition cause the rotor to stick inside the elastomer? If you run the pump dry, typically you're going to be doing damage to the elastomer that makes it harder. It's probably not going to stick to the rotor in that case. If it's pump off and it's actually running dry, you're going to see a very different failure mode. It's not going to be sticking like that, I don't think. There's certainly other things that can cause it to get stuck. Anything that's going to make that elastomer softer, again, fluid incompatibilities, aromatics, things like that. Anything that's going to make that rotor swell up, or the stator swell up and get soft is going to do that. But pump off, I can't see how pump off would lead to the rotor getting stuck. You're going to have pump failure, yes, if you're running dry for a significant period of time, but it's not going to get stuck. I don't think it's actually the elastomer is going to get hard and brittle and crack and break. It's going to be the opposite of getting stuck. It's going to be too loose now. So I don't think so. I don't know, Benjamin, you're on there. If you have anything different to say, you can certainly speak up.
No, you're right. Nothing to add on it. But pump off, yeah, generally cause the elastomer to burn, so you damage the elastomer is damaged, so you have the failure of the pump itself. But rarely the rotor stuck inside the stator. It's more due to swelling, but not really pump off.
Yeah. So I think that's all the questions that we've got here. How long is the recommended time to test bench after pulling? Well, that's again a very good question, and I know Bastien, if he's one of our service guys here, if he wants to comment on this, I'm welcome to get his input, or Benjamin as well. But I mean, for me, if you're in a situation where you've got CO2 in your wells and you're worried about explosive decompression, you've got two things you can do. One is either test that pump right away so you can see how it was performing downhole. But having said that, if you do that, you're getting good bench test information for how that pump was performing downhole. But 3 days later, there could be blisters in it and the pump is garbage. So if the purpose of the bench test was to evaluate it for reuse, that's no good. So it kind of depends on what your purpose for the bench test is. If you're evaluating it for reuse, I'd wait a few days and make sure that gas is all out and whatever blistering is going to happen has happened, because then you'll see that when you do your borescope and when you do your bench test. If you're trying to evaluate how the pump was performing in the well and you don't care so much about what it's going to be a week from now when you want to rerun it, if you want to rerun it, then yeah, testing it as quickly as possible would be the answer. So I guess that's a it depends type of answer there. I always seem to say that, but it's so often the case in this business. There aren't very many hard and fast rules. So next one, if I can't get a space out calculation, can I use the rule of thumb? If you can't, I would ask your pump vendor again for a rule of thumb for whatever pump model they're selling you. I mean, somebody sold you that pump and they've got to have the information for it. And because it's a huge, I mean, you saw the example I gave between the small pump and the big pump, 2 inches versus 8 inches. Well, if you're in a deep well, if you're 4,000 feet down, that's now 8 inches versus 24 inches. That's if you're doing too much, you're losing pressure capacity in your pump if you start pulling the rotor out of the stator too far. On top of that, if your rotor head is sitting above your stator, it's probably vibrating more. So you don't want to have more space out than you need. So I would be very hesitant to say, especially at 1 foot, that's an extreme case. So I'd be very hesitant to recommend using any rule of thumb that's not based on what your pump size is. So again, some of the companies might have this information published on their website, so you just find a similar size of pump. And when you're trying to find a similar size of pump, it's the OD that's probably the more important number to look at, more than the displacement for that. So find a pump with a similar diameter on somebody else's website. I think on PCM, I'm not sure, but I think our charts are on our website. I could be wrong. Bastien or Benjamin, you can correct me, but other companies probably have them too. So if you can find any company's chart for a pump of the same diameter, it'll give you more accurate numbers than using a rule of thumb out of nowhere. Again, contact your vendors. Whoever you bought that pump from should be able to give you that information. If you can't, contact us and we'll try. Even if it's not our pump, we'll try to give you something better than 1 foot per 1,000 feet. it's easy to do. So, like I said, if you have access to the software as well, that's whether it's the common one that everyone uses in the industry, or any company's proprietary software like PCM's PCM design, they can all do it. And again, just find a pump with a similar diameter, and it'll give you the same answer. Again, with the same rod size that you're using as well. So I hope that's okay. If there's not a downhole gauge to measure temperature, how can we protect the pump from working dry? Well, that's a good question. I don't trust temperature gauges for protecting the pump against running dry anyway, because I think they're, if you've got no flow going through the pump, a gauge at the pump discharge is not going to be measuring the temperature inside the pump. And nobody actually puts, well, I shouldn't say nobody unless they're doing science experiments, is putting temperature gauges inside the pump. So what you're normally using a downhole gauge for would be just intake pressure. Because if you have intake pressure and you have casing pressure at surface, you can calculate approximately how much fluid there is above the pump. So that's one of the best ways of protecting from running dry. But again, if you don't have a downhole gauge, you're looking at other things. One of them would be just fluid shots, using an echo meter to do fluid shots on a regular basis. And depending on how stable your well is, that depends on how often you're going to want to do your echo meter shots. If you know the well is really stable, then maybe you're doing a shot once a month or something like that. If you're ever going to speed the pump up, speed it up and then take several shots over the next few hours or a few days to make sure that you haven't sped it up too much. The other option that's based only on surface equipment would be a flow meter at surface. If you see that you're not getting the flow you expect, then that would indicate that you're running dry or potentially could be running dry. And the way that some of these automated systems will work, and you can do it manually as long as you have a measurement of the flow, would be to have a flow measurement and then speed your pump up a little bit, not very much, and see if you get increased flow. If you speed the pump up and you get increased flow, it means you're not pumped off. If you speed the pump up and you don't get increased flow, then you have a problem and you should probably reduce the speed. So those are a couple of things you can do between the echo meters and a flow meter, or I mean, some people will do the flow into a bucket as a flow test. It works. So things like that. Yeah, those are ways you can prevent the pump from working dry. Sometimes people ask if you can use torque to do that. So measured torque off your VFD, which is basically just motor current. I don't recommend it because I don't think it's sensitive enough to be able to accurately measure fluid level, but I know there's people out there that do it. I've seen a couple papers actually where people had downhole gauges and then they used the downhole gauge data to calibrate the motor current. So because they knew their gauges always failed before the pump did, so if they've actually got their downhole gauges there and they're calibrating the current or the torque data based on fluid level, once the gauge fails, then they can continue to use the torque data, which is, it's better than nothing. Okay, when the pump efficiency is low due to gas, will the reading for motor torque increase or decrease? And that is again an interesting question that could go either way. If the friction torque on the pump stays the same, then having gas in the tubing should probably reduce the load on the pump and reduce the torque. But is that if I had at the beginning, if the friction torque stays the same? If you had a lot of gas going through the pump, it can make the pump heat up, the rubber expands, and the friction torque goes up. So then which of these factors is dominant? Does the friction torque go up more than the torque from pumping the fluid goes down? Or does it go up less? It's again, this is why I said it's really hard to use torque to measure fluid level, because torque can change due to other reasons. So so again, like I said, if the friction torque's the same, then I would expect the torque to go down when there's gas in the tubing, but that if is the big problem there. What is a reasonable limit to how much gas a PCP can produce even if it doesn't gas lock? Yeah, so the PCP won't gas lock, yes. But we go back to one of the slides I had there about how low efficiency is too low. So again, it comes back to that question, do you have enough liquid going through the pump to keep the pump cool? One of the points on that slide, which I didn't actually talk about out loud, but it was on the slide, we talked about the pressure profile inside the pump. When you get a lot of gas in a pump, and there's been lots of papers out there from a few different sources that have showed this. So if you go into the SP and look at it, look at the One Petro database, you can find the papers. Email me if you want references, I can find them. But they show us a lot of gas in the pump. The pressure distribution inside the pump is not linear. The top of the pump does more work than the bottom. And because the top is doing more work, it gets hotter and it's more likely to fail. And then of course, once it fails, then the failure just progresses down the pump and the whole pump fails. So what you'd like to do is have something that makes that pressure profile more linear. So the whole pump is working evenly and you're not getting a hot spot inside the pump. So that's something that's useful as well. So the reason I'm talking about that is at PCM, we talk about our standard PCPs that we generally will give the rule of thumb, and again, it's probably as accurate as some of these myths that says 50% gas is the maximum. Some people will say 30. I say, again, it depends on how much liquid you've got and what's the temperatures. Is it water versus oil? Water, you can probably handle lower efficiencies than you can with oil because it absorbs more fluid. So, but again, somewhere in that 30 to 50% range. But if you can control that pressure profile more evenly, and again, PCM has this what we call the slugger, what used to be called the HR PCP. The point of that is that when you get gas fractions higher than 50%, it does help to linearize the pressure profile and make the top of the pump share the load with the bottom more evenly, and you get a longer run life. And again, our product data sheets we'll talk about going up to 95% free gas with that. But again, that's going to depend on having enough liquid going through it still. So you still have to have some liquid going through to cool it off. But yeah, so what's a reasonable limit? Again, with a standard PCP, generally people will say 30 to 50%. With a slugger, your HR PCP, it can go higher. Whether it's as high as 95 or not will depend on your particular application. But yes, you can certainly go higher with that. Comment on adjusting space out to adjust for landing angle. Says the software that you're aware of doesn't take this into account. Landing angle it definitely makes it difficult to do space out if you're a highly deviated well. What's difficult is knowing when your rotor has made it down to the tag bar. That's the hard part. If you can do that, the space out is actually the same. It's based on the pressure in the well, the pump geometry, and the length and diameter of the rod. But you have to be able to know when you're on the tag bar, and you have to have a weight indicator on your rig to be able to pick up rod weight again to whatever it was before you were on the tag bar. If you can do that, if you can tell that you're on the tag bar and then pick up rod weight to get your rotor to just come off the tag bar, then after that, the space out is the same. The software doesn't have to consider the other factors. So what the software is telling you, and same with what these charts that the different companies will have for giving space out, those are all the amount of space out you need after you've lifted rod weight when you've come off the tag bar. And also you should add in the distance between the tag bar and the bottom of the stator usually. So all these space out numbers are after you've done that. If you picked up your rod weight properly, after you come off the tag bar, then there's nothing more. Angle doesn't actually come into it any further than that. If you disagree with me on that, I'd be happy to have that discussion offline, because I'd love to hear your point of view on that. If I'm not clear on that, or if you disagree, but that's the way I've always understood it, and I've spent a lot of time looking at that. So I hope I hope I'm okay and not causing any controversy with that. If there's a risk of explosive decompression, do you recommend run and hold the pump only after borescope? Yes. Now, if you pull the pump out of the well and can just put it straight back in the same day, is that okay? Sure, but if you haven't borescoped it or pump tested it, do you want to take that risk? If you can't do it the same day, then yeah, you're gonna see potential damage. If there's CO2 in your wells or lots of gas going through the pump, I always use CO2 because it's the most likely gas to cause explosive decompression, but certainly other gases, including methane, can do it as well. Probably not as bad. But yeah, if you think there's that possibility, I would always want to run a borescope and probably a bench test if you're going to rerun the pump. So, what are good ways to avoid damaging elastomer decompression downhole during a trip? This again, during the trip, there's really nothing you can do. You can't be maintaining pressure on it while you're pulling it out of the well. All you can do is pull it at a rate that's not too fast. The slower you pull it, the better. Again, to do it to ensure you're avoiding it, you're going to be pulling it over days. But again, don't hurry either. Don't do it too fast. But beyond that, if the CO2 is in the elastomer, when you bring it out to zero pressure at surface, it's going to come out of the elastomer. And whether that causes explosive decompression will depend on how much, what's the pump geometry, what's the elastomer type. So there's other factors that go into it. So some elastomers are certainly better than others. And if you look at every PCP vendor, their elastomer selection charts have CO2 as one of the things they're looking at, and that's almost always related to explosive decompression. So within each of those vendors, you can see they've got some elastomers that are going to be better and some that are worse for CO2. So that's really what it comes down to, is choosing the right elastomer. And then if it's possible to avoid having gas go through the pump, that'll always be helpful as well. But once you're for pulling it, whatever damage is there, whatever CO2 is in the pump, it's already in there, and there's really not much you're gonna be able to do to prevent that during the trip. And like I said, unless you're willing to take a week to do it. When the rotor is too loose, can it still lift the fluid? Well, there's a good question. Depends on a few things. Viscosity, viscous fluids, you can use really loose rotors, no problem. If it's really loose on the bench test and you're taking it downhole, conditions can be very different downhole. So there will be a lot of people who size pumps that are zero efficiency on the bench test, knowing that once they put it downhole, it's going to get very high efficiency, or at least reasonable efficiency, because the elastomer swells up, either due to chemical action or due to thermal expansion, and then the fluid viscosity as well. So yes, loose pumps can work, and absolutely should be the right choice in some circumstances. Now, if the rotor is too loose after it's been sitting in the well for days and you're pumping, or weeks, so whatever swell is going to happen has happened and it's still too loose, yeah, you're going to have pretty low efficiency. Can it lift fluid? Probably, especially at higher speeds. If the pump is too loose, then yeah, running at higher speeds will help improve the efficiency. But can it lift fluid will depend on things like the pressure, the depth, the viscosity of the fluid. So I hope that answers it. Next question, how do you calculate pump intake pressure manually if there's no downhole sensor? You need to, the echo meter is your next option there. If you don't have a fluid level measurement, you've got nothing. You need to either have echo meter or downhole gauge. So with the echo meter, combined with knowing what the surface casing pressure is, or the casing pressure at surface, you can calculate reasonably accurately what the pump intake pressure is. Having said that, there are times when the echo meters are less accurate. The people the echo meter company will say they've got procedures to try to reduce these problems, things like foamy oil, and they can try to reduce it a bit. They'll do things like pressuring up the casing to try and suppress foam and things like that. If it's truly foamy oil, you're not going to get a good measurement of intake pressure from that. But if it's just gas bubbles in the annulus, yeah, the procedures they have can really help improve that accuracy. But that's one of the bigger problems is just foam or gas in the annulus makes it difficult. If you have a lot of gas being produced and you're taking the echo meter shot while there's gas production, you need to take that into account because the fluid density is a lot less than just the oil or water density once you have gas going through it. So you have to make sure you account for that when you're calculating your pump intake pressure. Yeah, with no a downhole gauge and no echo meter, you're just guessing. You've got nothing at that point. So that's where all you can do is measure your flow rates and see if increasing the speed increases your flow rate. Then at least you've got fluid above the pump. Did you try to do space out with the CFR run, and can we depend on it? I'm going to say yes, you can depend on it. But I might be biased in that because I spent 23 years at CFR before I came to PCM. So I think that the calculations that go into CFR are accurate for space out. Certainly, as with every software, everything has assumptions in it. But I think that the calculations that go into the space out are actually pretty good. I don't have any major warning bells that I would say about those calculations. Again, I mentioned before that it gives you the number of how far to lift up off the after you've lifted off the rod, picked up rod weight and lifted the distance between the tag bar and the bottom of the stator. It tells you how much more to do. So yeah, it's pretty good. Now it does depend on you've entered all the right well conditions into the software, right? So if you've entered a high fluid level, but it turns out that you pump the well off, yeah, you're going to need more space out than what was in the software. So again, you have to make sure that data is correct in there. Yeah, so I don't know what more to say about that. That's the last question. There's nothing else, Benjamin. Are we good? Oh,
just
one more.
Right.
With regards to explosive decompression, how would you manage the potential damage where a system is shut down for a short period but the pump is not pulled? Not much you can do with that, really. I think that most of the damage for explosive decompression, maybe not in all cases, but I think most of the time it's pulling it to surface that causes the problem. The biggest change in gas volume is going from 1 atmosphere of pressure to 0, bringing it to surface. So going from 2 atmospheres to 1 is like half the damage is going from 1 to 0, and etc. The more fluid you've got above the pump, more static fluid level above the pump, the less damage there's going to be. So it's only really wells that have basically very low reservoir pressures where they're seeing high pressure during production, high discharge pressure on the pump during production, but you go to 0 pressure during a shutdown, that you're going to have a real problem. Most of the time it's when you're bringing it to surface. But if you are in one of those cases that has very low pressure, really nothing more you can do. You can try and load the tubing with fluid, but it's probably just going to drive the pump backwards, and it's not going to stay in the tubing, so it's not going to help. So there's not a lot you can do. So again, thank you very much everybody for attending. I think we had over 50 people at one point. We're down to 41 right now, but again, good attendance, and thank you all so much for coming. If you have any questions that we didn't answer today, or you want to talk about, you've got your specific application you want to give some information on and get our opinions on, please send us an email. So I think my email is still on the screen there, and I sent the link to everybody this morning, so you should have my email that way. And again, we apologize for the link not getting sent. That was supposed to happen yesterday. Obviously, some technical difficulties. I don't know what the cause was, but again, obviously, anyone who's here got the link that at least the one I emailed. So you're all here, and again, we thank you for that. And again, any questions, please contact us. And if you have specific well information you'd like to have a pump design for, again, we have people here who can do that as well. And we can talk about your elastomer selection and with our experts here, or anything else you'd like to talk about. So yeah, thank you very much for your time, and just double check there's no new questions. Doesn't look like it. So all right, I guess that's it. So again, one more time, thank you, and goodbye to everyone.